Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
It gives me great pleasure to introduce Dr. Eric Ringer. Eric got his bachelor's degree in mathematics from Brigham Young University. I met Eric in 1992. We go back a long ways, the time of our PhD work, and we battled many snowy winters together at the University of Rochester. And from University of Rochester, Eric was at Microsoft Research from 1997 to 2005, and then went on to become an associate professor in computer science at Brigham Young University, where he directs the NLP lab down there. And more recently, he's joined Facebook. He's on leave from BYU, and he's here at Facebook as a research scientist. And today he'll be talking about how machines and humans can cooperate to find the truth about language. So,
it's great to be here. Thanks for having me. I'm here partly also to encourage you to consider Facebook for your career. It's a great place to work. If you love users, if you love people, if you love signals from people, I don't think that you can beat Facebook for having access to such amazing data and amazing problems. I'm actually not going to be talking about a Facebook problem specifically today. I'm going to be talking about some work that I did with students and colleagues while I was at Brigham Young University. It's work that I think is very meaningful. It's about trying to find the truth, at least in a very small, limited way, the truth about language and some language problems. I'll tell you more about those as we go. By the way, just a little caveat too, you might know that Facebook is famous for the motto, move fast and break things. I noticed that we also misspell things. On one of the flyers, engineering is misspelled. And so I just noticed that when we were laying it out on the table. I apologize profusely, but we just go for it. Similarly, this is the first time I've ever given this talk, so if there's some rough edges, I apologize also up front. But I hope that the ideas you'll find compelling. So let me acknowledge first the other contributors to this work too. Paul Felt, who's now at IBM Watson. Kevin Seppi, who's still at BYU. Kevin Black at Exactware. Jordan Boyd Graber at the University of Colorado in Boulder. And Robbie Hartel, who's at Google. All have made their mark on this work, and in particular, Paul. Facebook has a ton of text, images, and people, and I just want to say a little bit about this too. You might have noticed in the news that we recently crossed a line of having over 1 billion daily people using Facebook on average on any given day. Lots of other kinds of data around. I want to highlight in particular an announcement that hit the press also just a couple of months ago, this agent that we call M. And I want to use it just to highlight, as an example, to highlight the kind of problem that I'm going to be talking about today. M is this interesting conversational agent. It started with the technology that Facebook acquired from a company called Wit.ai. This is stuff that's been released publicly, so I'm not telling you anything secret. But M is an agent that tries to help you get things done. And you can ask it to do anything. Behind the scenes, there are some models that help analyze what you've said and parse the request, and also choose a reaction and a response and action to be taken. And so if this is done right, then the human trainers who are also there behind the scenes don't have a lot of work to do. If it's wrong or if there's a gap in what the machine is able to do, then humans step in and actually take action. And all of their actions are instrumented in such a way that over time the system is supervised to the degree that the system becomes more capable. This cooperation, I bring this out as kind of a great example of the kind of cooperation between machine and humans that's possible to help make machines more capable. So in a similar vein, I'm going to be telling you, I'll skip the quotes here. They say essentially what I just said. I want to tell you a little bit more about humans and machines cooperating to understand language, namely by using humans in the crowd, and hopefully in a way that minimizes costs so that we're not overusing the crowd. We're trying to use human resources, human knowledge about language as effectively as possible without having to ask too many questions. We'd like to save our money. I'm going to tell you about, in particular, the annotation aggregation problem. And I'll state my claim and show you a bunch of interesting models and hopefully some results that you find compelling for a few language tasks, and then draw some conclusions. All right, so annotated text corpora, we use them all over the place in natural language processing to do supervised learning. For example, if I want to understand public sentiment about something, I might manually annotate a corpus or get some help from the crowd. I'll train an auto-annotator, and then in the face of new data, I can make classifications. I can then assess, for example, aggregate sentiment geographically. You've seen papers of this kind. Sometimes manual annotation is necessary to help us get that good sentiment classifier, for example. I need to update my politics, obviously. This is old already. But assessing in real time the kind of sentiment about our politicians is something that we can then do once we've trained such an automated system. Similarly, we can assess support for different legislative measures or different candidates across the board. If we want to do question answering, there are a lot of moving parts in a question answer. If we annotate data for each of the moving parts in this system, then in the face, and we train it with something like Wikipedia and auto-annotate that, then we can build question answering systems on par, in some ways, with humans. So Watson, of course, famously competed with Ken Jennings, but behind the scenes, it was necessary to use annotated data to train a shallow parser, and a deep parser, and a logical form parser. Some of these things were also rule-based. They required human expertise of other kinds. Lots of moving parts, all of which required lots of labeled data. So yes, if we've got labeled data, we can solve some interesting problems. And I think that's well known and well understood. But it's also expensive. It's expensive to get that data. So today I'd like to attack that problem and try to minimize the cost. Talking specifically about the crowd, we are going to rely on data sources such as crowd workers who are giving us annotations through Crowdflower and Mechanical Turk. As you know, those annotations are cheap, but they're also noisy. We'd still like to get expert quality annotations without needing a lot of them. Let me paint an example for you. So here I've got 3 documents. And let's say that I've got a gold standard. I actually know behind the scenes, for the sake of this work, some gold standard that's been arrived at by an expensive process. In each data set, it's going to be a different process, but I've got high confidence in this. In particular, these are from 20 news groups, and the topics come from the news groups in which these documents had been posted. So I've got a sports label for document 1, politics for document 2, sports for document 3. I'm going to want to infer a label. Let's say that I don't know the gold standard, but I'd like to infer the label by asking crowd annotators. Let's say that annotator 1 and annotator 2 both annotate document 1 with sports. That annotator 1 is the only annotator who annotates doc 2 with politics, and then document 3 gets annotated in this way. Based on those annotations, we'd like to infer an aggregate label. And I also want to point out, too, here, in addition to paying attention to the labels, we'd also like to be aware of the content of the documents that we're labeling. If we're going to aggregate labels and try to do as well as the gold standard here, we want to not only look at the kinds of things that the annotators are saying, but the contents of the documents, too. So there are some terms here that are going to be particularly indicative of what the right label is. Our problem is to try to label these documents, to come up, to aggregate the answers, and to hopefully leverage the content of the documents, the features, to come up with the right labels. So we could use majority vote, right? We could say, hey, look, sports was the primary label on document 1. That must be the right answer. And that, it turns out, works quite well if you've got a lot of annotations. It's used in many kinds of tasks that we have available to us. But it ignores patterns among some of the annotator errors. It ignores the fact that some annotators are consistent with other annotators, or that they are out of step with other annotators. Some class pairs are more confusable than others. These are all problems that the standard approach, majority vote, misses. So we want to know, when will we have enough corpora? There's a lot of work to be done out there. Lots of languages, lots of domains, lots of tasks, from tagging to named entity recognition to semantic role labeling and so on. The cross product of these is a large set. And getting these right just by the old-fashioned, get lots of labeled data for all of them is not going to scale. So the primary claim for today is that by leveraging recent work in probabilistic machine learning, by modeling patterns in the data as well as among annotations, and by incorporating diverse annotation types, and that'll come at the end, we can improve upon the state of the art in annotation aggregation to produce better inferred labels, to get closer to the truth, using fewer annotations in a variety of document classification annotation scenarios. You'll see the kinds of problems as we go. So let's look back. In the literature, this is a Bayesian representation of a classical model called item response. We've got annotations down below. I'll actually step you through the model here in a second. Here we go. So I've got a distribution over a parameter vector theta, distribution over label proportions. I can sample from that a label for a particular document. Here I'm telling the generative story for this Bayesian model. I can choose a particular label, let's say Y sub n for a document, be it sports for document 1, politics for document 2, politics for document 3. Over here, I have a confusion matrix, for each annotator. For Alice, I've got a matrix. She tends to label documents which are truly labeled sports as sports, and sometimes mislabels them as politics, and vice versa for politics. And you can see the confusion probabilities there in the matrix. In the generative story here, I would generate those from the prior in the model there. And then finally, given a particular document, let's say document number 2, and an annotator such as Alice, then I can generate annotations. For example, she's annotating document 1 here with sports and so on. Likewise, Bill, he may be labeling sports, sorry, let me back off here. These are the annotations for document 1. So we're saying that Alice labeled it sports. Bill may have multi-labeled it. Here he's inconsistent. The model allows for that. So that's item response. It has a rich history. There's a lot of interesting work that went on with this model. The earliest piece from 1979 involved labeling images of the surface of Venus and volcanoes on the planet. It's been used for other kinds of problems as well, as you can see over the years. Variations of this have shown up. On the other end of the spectrum, I've got a conditional model, discriminatively trained. Let's call it log-RISP. It's reminiscent of logistic regression, and I'll point that out here in just a moment. So you can see that the label for the nth document depends conditionally on the data, rather than, as you'll see, I've got another alternative as well coming. So on this end of the spectrum, I've got my discriminative model, conditioned on the data. There's also a history behind this particular approach. Conditioning on the features of the data shows up in multiple publications in recent years. And then in between, I've got another generative model. Let's call it MOM-RESP. That's out of deference to mixture of multinomials, not to my mother. Here you can see that I have a generative story which involves both the annotations, the way that item response did, as well as generating data. And so in this model, both of those variables play a role in helping us come up with the truth, which is the labels for each of the documents in the corpus. So 3 different alternatives here. And again, this one has some recent history as well, some of which is ours. So this turns out to be a generative discriminative pair in the classic sense, in the sense of Ng and Jordan, for example. Here on this side, I've got naive Bayes forming the backbone of the model. You can see here with the label, the data, and then the feature distributions given the label. In this model, you've got logistic regression essentially forming the backbone of the model. Again, with the annotations hanging off to the side. So these two are a great pair to compare the two different approaches. Traditionally, it's been thought in the literature that the discriminative approach is superior, but you'll see that there are cases where the generative approach is actually better for doing annotation aggregation. All right, so Ng and Jordan remind us that parameter estimates converge in the generative case with big O log of the number of training examples. Logistic regression, the parameter estimates converge. The convergence is linear in the number of training examples. And this is a curve adapted from their paper, showing us that early on, we should expect that the generative approach should win out. But as we acquire more data, more examples, eventually the discriminative approach takes over. You can see there's some point of crossover there, where finally logistic regression wins. And if we've got noisy annotations, you're going to see that that crossover point might actually slide considerably further to the right. All right, so let's run a little experiment here. We used Crowdflower to ask people to go back and relabel 20 news groups, just as a sanity check for us to compare these two particular models. They had all of the same labels. We actually simplified them for crowd work, but these are essentially the names of the 20 news groups. We took 1,000 documents and asked for 7 annotations per document, which it turns out is a lot for this kind of thing. We don't actually need so many if we're smart about aggregation, but we'll see how this goes. It's very noisy. We only had about 50% agreement from the crowd workers, so we know that we're dealing with people who are not they're probably just fine as far as experts go, but they're not particularly conscientious, perhaps. In trying to aggregate these and comparing the result of the aggregated, the inferred label against ground truth, we come up with these results. And you can see here that the generative approach is performing quite a bit more strongly than the baseline, majority vote, and the discriminative approach, log resp. So we're going out, remember we annotated 1,000 documents, 7 deep, so by the time we get all the way to the right, we've got 7,000 annotations. And the accuracy against the original ground truth, again, is superior for the generative case. This kind of surprised us initially, but by referring back to that seminal work of Ng and Jordan, we were able to persuade ourselves that this makes sense. The generative approach wins early. The discriminative approach probably wins late, at least in this case. We'll see other cases where it can. But we didn't spend enough money to figure out where that crossover point was. The discriminative data model gives little advantage over majority vote in this case. And just a reminder that I'm showing you inferred label accuracy, not generalization accuracy. Let's draw a distinction there. Let me just sketch over here on the right to show you, or to help you think about what's going on here. If you think about the label Y, depending on the data X and the annotations A, early on we've only got a little bit of annotated data. The data, the features of the documents themselves dominate, and in the generative approach, those are sufficient in essentially a lightly supervised setting where we don't have a lot of labels, even noisy labels. Those are sufficient to help us get a decent model. I wouldn't call that a good model, but a decent model. Later on, when we have more data, then the conditional model should take over. The discriminative approach should win. Again, we don't show you enough. I'm not showing you enough to see that crossover point, but I would expect it to be further to the right. So it's an interesting example of a generative discriminative pair in the crowdsourcing setting. So let's go beyond this MOM-RESP model, this generative model that I just put on the table. When it's good, it's actually very good, as we just saw in this example. But when it's bad, as it is on this CADE-12 data set, it's actually horrid. It can lose significantly. We'd like a model that actually holds up better under fire across all kinds of data sets. This data set is a Portuguese news data set, pre-stemmed. It's particularly challenging. Won't say more about it, but if you want a tough case, this is a good one. We introduced a new model trying to get away from MOM-RESP here, in which we're essentially seeing a problem, and I'm trying to summarize very briefly the error analysis. what we needed is a finer representation of classes. And so as a result, we decided to use LDA, latent Dirichlet allocation, as the backbone of a new model. So you see LDA over here on the left of the model. Let's see. And you see the item response model still playing a role here, just like before in the others. So supervised LDA here on one side, with this y sub d being a response variable, which is predicted from as a logistic response conditioned on the topics, right? So for document sub n, we have topics z sub dn, and we predict this response variable y sub d. That variable is a characterization of the class. And then we are trying to infer, based on the topics and on the annotations, we're trying to infer that class, that response. Okay? So this is confused supervised LDA. It's like supervised LDA, but it's also confused because it doesn't have a true label. It doesn't have a fixed number here like you usually do for supervised LDA. It has only evidence, annotations, which help us infer that number. All right. And in this case, actually, we're doing a discrete version of supervised LDA. Y sub d is discrete, not continuous, as it is for the traditional supervised LDA case. OK, so let me just walk through the model briefly, just to give you some more intuitions. Over here, we have a distribution over vocabulary for a given topic T. Up there, we have, as before, a distribution over, this time over topics, not over classes. Here we have distribution over topics for document D. We have topics, one per token in document D. And then those are the tokens. And Z bar sub D is the aggregation of the per topic probabilities, one probability per topic. And it's those that are used in the regression here together. Here, I have a distribution over y sub d, the labeled response, given the topics and given the parameters eta. Okay? And again, this is logistic. So we use stochastic EM to do inference. We're simply alternating. We integrate out the priors and then alternate sampling on z and y and optimizing eta given z and y. This turns out to be a great model. It holds up really well experimentally. So let me just jump to some results here. First of all, here are the news groups, results on the news groups data. I've got accuracy here on the left and annotations on the right. This is number of annotations times 1,000 down here. And so we're working round robin through the data set. And as you can see, we're accruing a bunch of annotations by the time we get to the right. In this case, CSLDA is riding high on top, beating both MOMRESP, the multinomial model, the gold one, as well as the logistic model, that's the blue one, the item response model, and then, of course, our old baseline, which we're beating handily now. So we've got a new model that's in the generative family that does, I think, tremendously well at helping us aggregate annotations. OK. Then we've got another result here on the WebKB data set. Similarly, document classification. And again, CSLDA is holding up well, even though in this case, here you're seeing MOMRESP starting to lose to both the item response model, the green, and the logresp, or log linear model, the blue. Here you actually do get a real crossover point, unlike some of the other ones we saw before. Whoops. So you can see, when we get enough annotations, logresp is starting to come on strong, as we would expect it to eventually. But CSLDA is winning early at giving us great aggregation and holding up strongly as we continue to acquire additional annotations. What about that other data set, the troublemaker, CADE 12? You can see, as we saw before, that MOMRESP is down at the bottom, losing to the classic baseline, but CSLDA is riding strong up on top, giving us great aggregation. So again, helping us to aggregate the annotations that we've acquired here in a way that gives us hopefully a better picture of the truth, what the label of a document is given noisy annotations. There's some details here that I haven't spelled out, partly in the interest of time. It is the case that this is simulation. So we actually took the behavior of the users that we gathered from that original Crowdflower experiment, and we characterized the confusion matrices for those particular annotators, and then we created a pool of simulated annotators and consulted them in annotating the data. So we're driving all of these experiments that I'm showing you now as simulations to help us choose a promising model that's robust to the kinds of noisy annotators that you might encounter in the wild. Okay. I do want to point out a couple of things here. This table is intended to show you that we actually win in terms of cost, that it makes a big difference which model you use to do annotation aggregation. And so you see the model up across the top. You've got CSLDA on the left, momresp, logresp, itemresp, and majority vote. This number shows the number of annotations times 1,000. So in this case, 85 represents 85,000. The number of annotations which the algorithm reaches 95% inferred label accuracy. So what you see as you look across the board is that it takes those other models a lot longer to get up to that level. If you were to run those curves out further to the right, you see that these other models take a long time to acquire enough evidence to get to the point where you have a strong aggregation result. In some cases, we never reach 95%. That's where you see the dashes. In every case, on every data set that we tried, some of which I've showed you, some of which I hadn't, these are some additional data sets too, CSLDA is winning. And so we've got a strong competitor here for helping us aggregate evidence. CSLDA is our best foot forward at this point anyway. Okay. Now let's actually throw it at a real data set. This is data, it's hard to actually, let me get a caveat on the floor too here. It's hard to actually get lots of data sets, very many good data sets for which you have lots of redundant annotations from crowd workers, and for which you have some high confidence in the ground truth. There aren't a lot of data sets like that. This happens to be one of them, though. We've got people who were asked to label the sentiment about weather in tweets. And so we're applying our models here, all of the usual cast of characters that I've been talking about now, to this particular problem, trying to aggregate the truth about the sentiment in tweets. And so you can see that the models are still holding up. There's some interesting artifacts here which we could talk about later. But in general, you can see that CSLDA is still performing strong. The curves don't have the same shape as what we were seeing in simulation. And there's more to say and more to find out, actually, about those as well. OK. So for our discriminative model, we saw that it learns slowly. It takes a while to ramp up. But it makes few assumptions about the structure of the data. It actually is a good building block for us. And so we actually wanted to build on this. We wanted to use recent work in word representations to make logresp learn faster. We wanted to essentially give it the ability to generalize more quickly based on continuous representations of the documents that we're dealing with. So this is an attempt to actually make logresp do better, leveraging some more recent work in text representation. So of course, you know that if you try to represent a document using a one hot vector, right, one word, one position represents the presence of one word in your vocabulary. There's bacterium, there's cactus, et cetera. That's a sparse representation, but we use our word embeddings as a dense representation. Lower dimensions located densely with one another in this lower dimensional space. So bacterium, for example, might have this much smaller representation in that dense space. I've got bacterium and cactus again. We know how to train these vectors. We could go to Wikipedia and use off-the-shelf Word2Vec software to choose to learn representations of the words. If we start that way, let's see what happens. Let's put this idea together with logresp and see where it leads us. So you remember that word representations are compelling partly because their location in the space is relative to one another, is indicative of meaning. If I just, I'm sure most of you have seen this, but just in case you haven't, let's say that you've got the word bacterium, the singular here, and bacteria down to the left. I've got cactus, the singular here, and cacti. For the sake of, sorry, I'm pointing at the wrong screen again. I apologize for that. Cactus up here to the right, cacti down below it to the left. If you were to guess where women would be located, the vector for women in this space, naturally you would expect it, of course, to be down and to the left. Again, this is just an illustration. But if you look at the data, if you look at the relative positions of vectors that have been computed from software like Word2Vec, you get this kind of phenomenon. As a result, you're able to represent documents, for example, naively as the sum of the vectors, the word vectors, for the words that constitute the documents. Okay. If we use word vectors in combination with our logistic regression model, we actually get a very interesting result as well. So here I've got my cast of characters again, and I've got logres plus Word2Vec. That's the red one on top. And you can see that even though I'm not beating CSLDA or even MOMRESP in this case on the newsgroups data, I am doing better than the old logistic regression, the old logresp logistic regression-based aggregation model. So that's a nice thing to see. But we already knew that the generative models are well suited to this particular data set, the newsgroups. And those are the ones that I was just pointing out. Logresp doing better with dense representations instead of the sparse representations. If I go back to the weather set, though, you'll see that, in fact, in tweets, you've got all kinds of crazy stuff going on. Most of you are probably Twitter users. You know that the kinds of tokens, the kinds of symbols that are being used in tweets are sometimes surprising, sometimes unexpected, but perhaps similar to symbols that you would have used in similar contexts. As a result, whereas some of our earlier models might not be able to deal with all the out-of-vocabulary symbols, it is the case that when I use the embeddings, I get a better representation for some of these infrequent, strange symbols, and as a result, I get better inference and better aggregation because I've got a better signal coming out of the features of the tweets. So again, the usual cast of characters, but this time on this data set, you see that our new model, logresp with the embeddings, is doing even better than the others before them. So the promise of using these representations comes out, especially when you're dealing with data like Twitter, and not the more normal data that you encounter in something like 20 newsgroups. So again, a nice result on a real data set. Okay. So a few labels there. You can see that for this, there's a big win here from logresp up to logresp with Word2Vec. And here we're using document embeddings in the way that I described before. Okay. So I've claimed that discriminative models are flexible. Let's try something different. Let's try another data set. This is a word compatibility task. Again, we weren't the source of this data set. This comes from Krzyzewski and Baroni. They did the work of going out and soliciting lots of redundant annotations, more than is necessary, with high confidence settling on a gold standard. We're using that gold standard as our point of comparison for computing inferred label accuracy. And we're trying to do it without having to use as much over annotation as the original task. Here's the task. We say that words W1 and W2 are compatible, semantically compatible, or compatible for this task if they refer to the same real-world entity. So any annotator has to decide, given two words, are these the same thing? So in this example, in the data, we've got bird and starling. For the sake of this task, that was true. I can imagine reasons why you would not want to answer true there, but that's okay. I didn't define the task as it was originally constructed. Rock plus meal, in this case, false. Father plus carpenter, true. Again, I don't know the full context for why that would be true. I have my own questions about this answer. But that's the task. We aren't analyzing the topic of the documents. We're actually trying to compare semantic meaning, right, of a word pair. And so we don't really have a good generative story for this. Generative models just don't work. Not only are we hopeful about the dense representations here, but we just don't even have a way to tell a generative story to solve this task. You might be more creative than I am and be able to come up with such a thing, but I don't have a generative story. And so I don't have a generative model. But we can use our log resp on word comparison vectors. So let me tell you what we did. We put the words into, we represented the pair as a vector. So you've got the cosine distance between the word vectors for the two words, word 1 and word 2. You've got the L1 distance, the L2 distance, and principal components as well. So we've got all kinds of interesting things in this vector. We did some feature analysis too, but I won't show you all of that work, just to present this as simply as I can here. So for this compatibility test, you can see we compared item response, just as a strong baseline, the original approach that we started with that isn't sensitive to features. Majority vote, which also is not sensitive to features or to the kinds of agreements and disagreements and consistencies that happen in annotations. And then we've got our log resp with word embeddings. And you can see that log resp with word embeddings actually starts out better than the others, but eventually item resp catches up. There's not much room to beat item resp here. But early on, with a small number of annotations, it seems to be the winner. Okay, so that's just a data point, something for you to consider. It's this new technique at work on a task for which we don't have a generative model of the content, right? Item resp didn't require a generative model of content. It was just a generative model of annotation. Okay. In other words, mom resp and CSLA weren't even on the table because they weren't options for us. Here's another task. Shu et al. Came up with this task. It's the Twitter paraphrase task. It's exactly what you would expect. Do tweets T1 and T2 convey the same information? So here's an example. Star Wars Return of the Jedi is on, and my favorite Star Wars movie is on. The judges say that's a paraphrase. If your favorite Star Wars movie is Empire Strikes Back, then I can't explain this example. Okay. And then you're deciding also, let's say Star Wars Return of the Jedi is on versus, and of course, because I drink and like Star Wars, I know nothing about football. So it's a completely different idea. That's not a paraphrase. Okay. That's the task. Apply the same approach. I don't have, there exist generative stories for this task. Let's keep it simple. Without a model that has without a generative model, again, we're just comparing majority vote, the non-data sensitive model, item resp, and then this new conditional model that's conditioned on the dense representations of the tweets. We end up with a really nice, strong result aggregating the annotations for this task, the Twitter paraphrase task. So you can see that the approach is quite flexible. We think that this is a compelling way to aggregate annotations for non-trivial problems, even like this one. So humans do have a lot of knowledge about language. We'd like to use it all. We'd like to use it to train classifiers. We'd like to use it to train sequence labelers. We'd like to use it to train shallow parsers, maybe even deeper models. There's some great work going on here involving annotating semantic parses, for example. How do we get that knowledge from the users? That's one of the interesting puzzles. We can either ask experts who are extremely good at these things, or we can continue trying to ask non-experts. That's the name of our game right now. So again, we can get labels on instances. We can train our models on the labels. But there's been more recent work that develops models that learn from diverse kinds of knowledge, not just label annotations. So for example, here's a fun Christmas sweater example. We've got a bunch of comments about the sweater. Loved it, got it for ugly sweater party. And we've got positive examples, right? We've got negative examples, and then it looks like mixed examples, right? Nice material, but a bit thin, and sizes are a bit small. That's a mixed response. You've got some positive and some negative in there. Traditional annotations are just labels on the tweets, let's say, or labels on the comments. Let's say these are comments about the product. But we could also imagine labeling features, right? Things that might actually hold up across lots of labeled examples. So we've got positive features, like perfect, comfortable, durable, et cetera. We've got neutral features, like okay. We've got negative features. If we could label features and take advantage of those, not instead of instance labels, but in addition to instance labels, then we might be able to draw stronger conclusions. There are some great approaches for doing this kind of learning from just a few examples, a few labeled examples, a few labeled features. The whole paradigm is sometimes referred to as lightly or weakly supervised learning. And there's some great approaches out there which have been shown to be interrelated to one another. If you squint a little bit, not at this picture, but at the ideas, then the measurements framework that was introduced by Percy Lang and his co-authors, sort of the conceptual progenitor of some of these other approaches. The others can be seen as special cases of the measurements framework. But in practice, all of them assume input from a single infallible human. And so instead, what we'd like to do is look at the measurements framework, but also think about using lots of noisy annotations from the crowd. So let's talk about an approach that we're thinking of as measurements in crowdsourcing models. What's a measurement? Well, you can think of it as the kinds of things I was talking about before, just as examples, right? Labeled instances, labeled features. So we take a measurement K from annotator J that could consist of her prediction of the value tau sub jk of a measurement function, sigma sub k xy. Again, that could be a labeled feature or a labeled instance, summed over the entire data set, okay? With some thought, you can define these sigmas to let you handle a huge diversity of inputs. We've got a new model called the per annotator normal model. In the interest of time, I'm going to go into fast forward mode. I apologize now. We take advantage of our labeled features. And to cut to the experimental chase here, you can see that I'm comparing against item response. That's the IR there. So this is the same model we were talking about before, one of our simplest probabilistic baseline, and majority vote, MV. And you can see that this model, again, per annotator normal model, applied to the newsgroups data set, allowing us to label all kinds of interesting features and instances, is giving us a steeper slope, a faster learning of how to aggregate annotations. So this is another competitor that's, I think, worthy of consideration. It also allows us to ask questions like, which feature should I annotate next? Or who should annotate this next? That leads us to active learning kinds of questions. Again, applied to the weather tweets, sentiment about weather tweets problem. Again, we get a nice result there. Okay. We also have measurements involving labeled locations in that dense space. Also another strong result. Summary guidance for the practical-minded. If you've got a suitable generative aggregation model, a generative story, then use it. CSLDA is a great candidate for doing aggregation if you are able to tell a generative story for your data. Otherwise, use a discriminative model with a dense semantic vector representation. And then also consider incorporating multiple annotation types. That was the last piece. So I've shown you some models that are new to this work. MOMRESP is new to this work. LogResp is new to this work. Both of those use variational inference. The comparison of the generative and the discriminative annotation aggregation or crowdsourcing models, that's new to this work. CSLDA and its inference, that's new. And then the application of word embeddings to challenging aggregation problems. As far as we know, this is the first time this has been done. And then also this model that I hit fast forward on, the per annotator normal, is also a new model, a new approach to doing annotation aggregation, a new approach to trying to find the truth about language by asking annotators for some help. There's a lot of good data sets here. If you'd like to try your hand at this, if you'd like to try to beat all the models I just put on the table, the data's there and you're welcome to use it. And there is some future work we can talk about, but I won't enumerate all that right now. I'll just stop right there and open it up to questions. Thanks for your attention and for your patience.
Okay, questions?
That's okay. I'm going to monopolize for a second then.
Well, maybe you could go through your active learning.
Yes, happy to do that. So I'll tell you, Facebook has awesome opportunities in machine learning and in NLP. There are several groups working in this space. There's also a lot of great data science going on. If you care about signals from real users at the scale of 1 billion plus users, and would like to consider opportunities of working at Facebook, please come do talk to me. I'd love to help you either start making career plans or even just testing the waters with an internship. We've got great internship opportunities for students at all levels, including PhD students. So we'd love to have you come work with us on some of the interesting problems that we've got on the table, whether that's in search or in content discovery or in understanding users. Great opportunities. So please do come talk to me. There's also some contact information on those flyers back there, including the one with the typo on it, the egregious typo. Okay. So in this particular experiment, we're trying to know which user should we ask, which annotator should we ask. And we're running on weather tweets with both document annotations and labeled predicates. So labeled predicates you can think of as features, right? Labeled features. And so the algorithm jointly selects the annotator and the annotation type. Should you label an instance or a predicate? Yes. And then finally, I'll skip the last bullet, but you can see here that if I randomly select, this is the standard active learning baseline, random sample selection, then over time, the number of measurements that you take, randomly selected, leads to gains in accuracy. But if you select more intelligently according to your crowdsourcing model, then the curve grows more quickly. And in particular, for example, for a particular accuracy level, let's say 90%, if you draw a horizontal line there, you can see that the cost savings over the random baseline are significant. So this particular formulation of the active learning problem shows you that a crowdsourcing label can be used to actually choose the kinds of questions you ask if you want to learn more about your data. And it's reflective of the content of the data and reflective of the past behavior of your annotators. So that was punchline. Yes?
I'm curious if the models that are doing better at inferring the true labels are also doing better at inferring the characteristics of the annotators.
Yes, I didn't actually. I'll pay you afterwards for that question. I didn't put enough emphasis on that. Let me just skip forward, back to the beginning here and just bring up one of those early models. Just good old item response. You see that the only observed variable here in the model, the colored in one, is the annotations. The labels, the per document labels need to be inferred. They're not colored in, they're a hidden variable. And the annotator confusion matrices are themselves hidden variables. By the time we're done doing inference in the model on the annotations, not only do we have a guess at the label, but we also have a guess at the kinds of confusions that the annotators are making. And as a result, we can make determinations about which annotators are doing a great job and which ones aren't. So we actually learn a lot about these annotators, and the same can be said, again, skipping forward here. Let me put all three of those models side by side. You see they all have that same y sub n, or label hidden variable, and they all have the same gamma sub jk hidden variable, or in other words, the per class, the per annotator, per class confusion vector. Collectively, per annotator confusion matrix. So we do learn a lot about them, and the more data we have, the better. I have some good experimental results in a paper that I could point you to. It was actually the paper that introduced MomResp. Yeah, the short answer is yes. We learn a lot about the annotators. I actually don't know. We didn't track that closely enough as the models evolved. We were staying focused on that inferred label accuracy metric. That would be worth looking at. That's totally a good question.
Okay, Richard.
Do you validate the synthesized data from real data and real data? So a lot of your charts show synthesized data.
Yeah.
How do you validate that? Why is that? Why should we believe it?
Right. So the question was, why do we believe the experiments I showed you that involve simulations? And the answer is that, remember, initially we ran this crowdflower experiment. This was real data. It allows us to come up with models of users, of annotators. And we were using those models of annotators to help us drive the other experiments, which we couldn't afford to run with real users, so we needed to run them in simulation. The validation of those initial experiments comes when I apply the models to the real data sets, like the sentiment tweet problem, not synthesized, but real data, to the word compatibility problem, again, not synthesized, but real data. And then finally, the tweet paraphrase problem, again, real data. So those three tasks, real data. And in those three tasks, the models that we designed to try to address those problems and had first selected in simulation were now working successfully on real data. So that was our validation. That was the rationale for deciding that the initial experiments at least steered us in the right direction. Yeah.
Any more questions? Okay, let's thank Eric again.